Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to look at how to find the area of a sector of a circle and the length of an arc. I think you probably know what an arc is, right? We've talked about that before in this unit, but you may not know what a sector is. So we'll go over that vocab and then we'll teach you how to find the areas of sectors and the lengths of arcs. We are going to skip number 1, that do now. We're going to jump right into some terminology, some vocab. So we need to talk about what a sector is and then what an arc length is. A sector of a circle is a region bound by two radii of the circle and their intercepted arc. So, hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to focus on finding the area of sectors and the length of arcs. And we'll get into, we should know what an arc is, but we may not know what a sector is. So we'll get into that vocab in a second. But first, let's kind of open up our brains a little bit, get them in gear by doing this do now. So this question says, find the measurement of arc TR and the length of segment UQ. We can assume that TQ is a diameter. We're going to round the side length to the nearest tenth. So go ahead, pause the video, see if we can figure out the answer to both of those questions. And then we will have a quick discussion before we jump into a new lesson. Okay, so the arc length is very straightforward. We're looking for the measurement of arc TR. We also know that the measurement of that arc is going to be equal to the measurement of the central angle that intercepts that arc. Right? So if I can find the measurement of this angle, I'm going to know the measurement of that arc. And I know that if TQ is a diameter, oops, need my curve line tool. Both of those angles should add to 180. Right? So the measurement of angle S plus 126 is equal to 180. We know that the measurement of angle S is equal to 54 degrees. And the measurement of angle S, to be fair, it's actually that middle point that's called S. So I should call this TSR. Just the way I drew that red, it looks like that S is what that angle is, but technically that S is the center. So I'm going to leave it as measurement of angle S. I do realize you may have a concern. Why am I calling this by just one letter? Because that S is a point. Well, I'm explaining why now. So measurement of angle S is going to be equal to the measurement of arc TR, right? Because if S is the central angle, it's got to have the same measurement of that arc. So if the measurement of S is equal to 54 degrees, well, by the transitive property of equality, right, I know that the measurement of arc TR is equal to 54 degrees. So arc, very easy. Segment UQ, a little bit more difficult. I'm looking for this orange segment right here. Couple things I know. I know that this angle right here has to be a right angle, right? Because we know that both of these together should be 180 degrees. And I know the length of my radius. I know the length of my radius is 4. So if I know that that's a right angle, and I know two sides of that triangle, right? This actually forms a right triangle. Well, I can just use the Pythagorean theorem, right? So I can do 4 squared plus 4 squared is equal to UQ squared. I don't know why I said this was a lot tougher. It's really not. I mean, maybe the algebra is a little bit more tough, but still just one equation. I get 16 plus 16 is equal to UQ squared. 32 is equal to UQ squared. And we're just going to take the square root of both sides. It does say to round to the nearest tenth, so I don't have to worry about simplifying that square root. I'm just going to put it into a calculator. And I'm going to get nearest tenth, about 5.7 is approximately the length of UQ. Okay, enough with the do now. Let's move on to some new vocab. A sector of a circle. A sector of a circle is a region bounded by two radii of the circle and their intercepted arc. So if I look at this circle over here, I have a radius here, and my arc, my intercepted arc is A to B. So all of the area inside of this figure, doing it in purple, that's what we call a sector. So a sector is bound by an arc and two radii. And we're going to name a sector using three letters. The places where it intersects the circle, so A and B, as well as the center of the circle. Arc length is just the distance along an arc measured in linear units. So we've measured arcs in degrees, right? Let me do another diagram over here. If this is my circle, and let's say my central angle is a right angle, I'm actually going to write the 90 degrees in there. Well, that tells me that this arc, let's call it AB, the measurement of arc AB is going to be equal to 90 degrees because it's got to be the same as the central angle that intercepts the arc. Now, if I'm talking about the arc length, that's not going to be measured in degrees. That's going to be measured in something like centimeters or meters or inches, something like that. So it's actually going to, you could think if this circle was a piece of string, right? So let's just do this in orange, right? If I went all the way around the circle with string and I just cut out the red piece of the arc of the circle, well, if I laid that piece of arc flat, right? So if I took this red piece and I just laid it flat, pretending it was string, right? I could find a measurement for it. And we'll see that we don't actually have to do that, right? We don't have to actually take string, lie it flat, and measure with a ruler. There's ways for us to figure out the measurement of that just using some formulas. And we'll kind of derive those as we move throughout the lesson. But that's what arc length means. The measurement of an arc, going to be measured in degrees. An arc length, going to be measured in something like inches, centimeters, something that we would measure a segment with. Okay, let's keep going. Again, our goal today is to develop these formulas for both sector area and arc length. So we're going to first start with sector area. Take a look at this. Let me see actually how much I can squeeze in. It's probably too much. Maybe I can get to there. Okay. It says, what ratio of the circle below is shaded? How do you know? In your explanation, think about the shaded area's relationship to the whole, and you can think about using their degree measures. You don't just want to say it looked like 1/2, 1/4, etc. You could do the same thing with the circle that's shaded in purple. You're going to think about what is the ratio of the purple shaded area compared to the whole. And we're just going to write a ratio, right? You can write a ratio many different ways. We're going to choose to write it as a fraction. So I want to see your ratios as fractions as the part that's shaded compared to the whole. So pause the video so you can come up with both of those ratios, and then we will have a discussion. Okay, so for the first one, maybe you are thinking in your head it's got to be 1/4, right? Well, it is 1/4, but how do we prove that? How do we prove that the actual green shaded area is 1/4 of the circle? Well, we can see this little 90-degree angle in here, right? So 90 degrees is the measurement of the angle that's shaded, right? This is a sector right here. So the measurement of the angle that forms this sector is 90. The entire circle, well, that's going to have a measurement of 360. So our ratio of the shaded to the whole is 90 degrees over 360 degrees. That does give us our 1/4. For the purple, it's not actually clear what the ratio should be, well, what the simplified ratio should be. But if we follow the same steps of shaded to the whole, we're going to get 135 over 360. And then we're going to simplify. Well, those are both divisible by 5. Try to come up with the greatest common factor, though. It's not 5. In my head, I was thinking it was 15, but it's actually not even 15. There's a number larger than 15 that goes into both of those numbers. That number ends up being 45. If I divide 135 by 45, I get 3. If I divide 360 by 45, I end up getting 8. So that purple shaded area is 3/8 of the entire circle. Okay, so if we want to write a ratio for any sized sector of a circle, how could we do that? Well, if we let n be the degree measure of the central angle that forms the given sector, it's going to be m, because our shaded goes in our numerator, over 360. Right? That will give us the ratio of what the sector is compared to the whole. That's going to be important in developing our formula, because we need to know what part of the whole the sector is. So we're going to hold on to that. We're going to keep going. We're going to look at number 4 now. So it says, suppose a circle has an area of 90 centimeters squared. So the whole circle area, the whole circle's area is 90 square centimeters. And the measurement of a given sector is 110 degrees. So essentially we have a circle here. And this angle right here is 110. That's for the sector that we're trying to find the area of. Can we set up a proportion, or can we set up an equation where one ratio is the measurement of the sector to the whole circle and the other is the area of the sector to the total area? Now that's a lot of words, and I think before I just put this up here, I want you to try to figure it out. And maybe you won't even need to set up a proportion. There's other ways to do this other than a proportion. But if you know that the entire area is 90 square centimeters, could you figure out the area of the purple? So 90 centimeters squared total, area of the purple, that's our goal. So pause the video, see if you can do that, and then we'll have a discussion. Okay, so let's set it up based on this proportion that they're talking about, that they mentioned. So proportion is just one fraction equaling another, right? And then we can usually cross multiply to solve. So one of these ratios is going to be the measurement of the sector to the whole circle. Well, the measurement of the sector is talking about the angle measurement of the sector. So 110 degrees of the sector to 360 degrees of the entire circle. Well, that ratio has to be equal to the ratio of the areas. So I'm looking for the area of the sector, right? We'll just call that x. And the entire area is 90 centimeters squared. So that's what that proportion was talking about, right? On one side, we have the proportion, we have the ratio of the measurements, and then we have on the other side the ratio of the areas. And by cross multiplying, we can solve for our unknown. I'm going to get 360x. You can leave the degrees on there. You don't have to. They're all going to simplify out in the end. We'll be left with centimeters squared. Maybe just let me show you. That way you don't have to just take my word for it. You can see it in action. 90 centimeters squared times 110 degrees. That's going to give us 9,900. And this is going to look weird, but degrees times, I'm not actually going to draw it like this. Let's see how I want to show you guys. So we are actually going to leave it like this. Degrees times centimeters squared. So I know it looks weird, like 9,900 degrees, but it's not like the degrees is being directly applied to the 9,900. We're not saying that there's 9,900 degrees. What this reads over here is the number 9,900 times degrees times centimeters squared. And when I divide both sides by 360 degrees, well, the degree units end up simplifying, right? Of course, the left side simplifies, but the degrees on the right-hand side simplify. We're going to be left with centimeters squared because there's nothing to simplify out the centimeters squared in the numerator. And then we just divide the two numbers. So 9,900 divided by 360, that gives us 27.5. So you don't have to keep the units on there if you understand that they're going to simplify out in the end. I just want to show you why we're allowed to do this and how the units end up coming out correctly at the end, right? We want to end up with centimeters squared because that's the units that x has to be in, and everything else simplifies out nicely. Okay, this makes sense, right? 27.5 is less than 90, and we know that the area of a part needs to be less than the area of the whole. This is how we can do it, though, right? This is going to be how we figure out the area of any sector of any circle. Set up the ratio of the degree measurements of the sector compared to the whole, and then equal that to the ratio of the areas of the sector compared to the whole. Let's do one more. Let's just do number 1. See if you can figure out the area of that black sector. Okay, so ratio of the degrees, right, would be 36 over 360. We don't actually know the area of the entire circle, right? This time they just give us the radius. Well, hopefully we remember that area of a circle is pi r squared. So area is equal to pi times the radius squared, so 16 squared. That means area is equal to 256 times pi. Now, I'm not going to simplify that now. I'm just going to put that in as the area of the whole circle, 256 times pi. And we'll do our rounding at the end. Right, so we'll keep it in terms of pi for now, and at the end we'll round. Let's make this x. That is the area of our sector. Time to cross multiply. (36 times 256). It's going to give us 9,216 times pi is equal to 360x. It does say round our answers to the nearest tenth, so just be aware of that as we divide both sides by 360. And we should get approximately 80.4. Let's think about our units. Radius was in inches. That means the area is going to be in inches squared. That's going to be the area of this sector, approximately. Should have approximate equals signs there. Okay, we will hold off on number 2. We'll do that in class. And I think we need to talk about arc length now. But you're going to notice some strong similarities between our formula for arc length as well as our formula for sector area. Number 1 says, what is the ratio of the given arc, FG, to the circumference of the circle? Think about how you determine the ratio for sectors and approach this in the same way. Well, here's our arc, FG. Remember, if they just use 2 letters, we have to do the minor arc, so the shortest distance. Well, that arc has a measurement of 134 degrees. So 134 compared to the total, 360, and we just need to simplify. Off the top of my head, it seems like not 4, not 6, not 8. I'm going to say 2 is the greatest common factor. So we're going to get 67 over 180, and we're not going to be able to simplify that ratio any further. 67 over 180 would be it. We could do the same thing for number 2. Go ahead and do that. Simplify as much as possible. What's the ratio of arc GH to the entire circumference, or the entire circle? Well, for this one, we have 40 over 360. This one does simplify pretty nicely. Greatest common factor here is 40, so I get 1 over 9. So maybe you see where we're going with this, right? I'm developing the ratio of the individual arc to the entire circumference, right? The entire distance around the circle. And that will hopefully let me figure out the length of that specific arc by setting up a similar proportion. So this is going to be the same as what we did up above. If m is the degree measure of the arc, well, the ratio of the given arc to the circumference would be m over 360. Let's look at 5. It says, suppose a circle has a circumference of 56 centimeters, and the ratio of the given arc to the whole circle is 3/4. How could we find the length of the arc? Try to set up a proportion where one ratio is the measurement of the arc to the whole circle, and the other is the length of the given arc to the total circumference. See if you can set up that proportion, just like we did for sector area. This one's nice because we don't have to, they give us the measurement, or they give us the entire circumference, so we don't have to use a formula to find it. And then solve to figure out what the length of that arc would be. Okay, so it tells us that the ratio of the given arc to the whole circle is 3/4. So 3/4. Who knows? Maybe that, well, we actually do know. The degree of that arc then, right, must have been 270, because 270 over 360, that's what gives us the 3/4. So they even did an extra step for us, a couple extra steps. This is also, on the other side, we're going to have our unknown. That is the length of the arc. And in the denominator, right, we're going to have the entire circumference. So just like with sector area, we did the area of the sector compared to the total area of the circle. Here we have the length of the arc compared to the entire arc, right, which is the circumference. So if you think about, going all the way around the circle, you could think of that as the entire arc of the circle, but we have a special name for that, right? We just call that the circumference. So I'm actually going to erase what we have, but you can just write it next to it if you want. The length of the circumference, they give it to us, right? They tell us that it is 56 centimeters. So now it's time to cross multiply. 3 times 56, that gives us 168 is equal to 4x. Divide by 4, that gives me x is equal to 42. Let's put our units there. 42 centimeters. Quick visual for those of you that would like it. If I have my entire circle, right, we'd essentially be talking about this arc in pink, this portion of the circumference. So if the entire circumference was 56 centimeters, that arc piece would be 42 centimeters. We should also put a right angle here, right? If that's 90, there is our 270 degree angle. All right, I think we have time for one more. Let's do one where you've actually got to find the circumference yourself. Let's do number 1. So again, just like our last example with sector area, in this case, the circumference is not given. So you're going to have to figure that out. But the proportion method is still going to work, right? On one side, ratio of the degrees, the measurements. On the other side, ratio of the arc lengths. So pause video, give it a shot, and after this, we'll be done. Okay, so let's just go ahead first find the circumference, because we know we're going to need that. Formula for circumference is C for circumference is equal to 2 pi r. Here, 2 pi times the radius, which is 10. So my circumference is 20 pi. I will just keep that and I will work with it and round at the end. So our proportion here, well, as far as the degrees go, we're looking for this arc DC that has a measurement of 90 degrees. The whole circle is 360. I do not know the length of arc DC, so that's my x, but I do know the length of the circumference, or the value of the circumference. That's going to be 20 pi. So again, setting up these proportions is the main thing. If you can set a proportion up, we should have no trouble solving it. So I'm going to get 360x is equal to 1,800 pi. And then we'll divide both sides by 360. I do believe it says to round to the nearest tenth again. So we have 1,800 pi divided by 360. That gives us the length of that arc is approximately equal to 15.7 feet. Don't forget your units. If you want notation for the length of an arc, we just need to write out the word length. So we would say length of, you can either write the word out, arc, or you can just put the little symbol, arc DC. For measurement of an arc, we do have the little m, right, measurement of arc DC, but that's going to be if we're measuring it in degrees. If we're finding the length, we're just going to write out the word length. All right, again, we're pushing about 30 minutes, so we'll cut it off there. Plenty of problems that we will get to in class. Feel free to take a look at them if you want. There are some challenge problems down here. I'll just give you a quick glance at those. I guess first, these formulas for sector area and arc length. We'll talk about those. All that is rearranging the proportion we came up with. The proportion method, that's how I would think of this though, right? One side of your proportion is the measurements. One side of your proportion is either the areas or the circumferences. We may talk about, an actual formula we can memorize in class, but I think intuitively understanding those proportions is going to be the best for us. The only thing we haven't covered in the video would be the areas of segments of circles. And this word is a little deceiving because a segment of a circle is a region bounded by an arc and its chord. So it's not a segment in the terms we generally think of them. This right here would be the segment of a circle. So we'd be trying to find that area. Again, not a topic for this video, but I think you could probably figure out how we do that. This would be like a composite area problem, right? Where there's not just a single formula for it. You've got to use multiple formulas and either do some addition or subtraction. But we'll hold off on that. Again, we'll stop the video here. As always, enjoy the rest of your day, and I look forward to seeing you for our next lesson.